Greetings of the day to all of you. In today's lecture, we are going to discuss advantages of shunt compensation. We have already discussed various methods of compensating a long high voltage transmission line like shunt compensation technique, series compensation technique, and compensation by phase angle control. What are the advantages of these compensation techniques? So first of all, we are going to discuss advantages of shunt compensation. Advantages of shunt compensation. Now, I have already given you an idea about what are the various advantages of shunt compensation, like a shunt compensated transmission line has larger power transfer capability, or power transfer capability of this shunt compensated transmission line increases. So first is increased power transfer capability. Power transfer capability of transmission line, of course. In this context, we already know that for an uncompensated transmission line, what is the power which is transferred over the line? It is simply given by V square by X sine delta. And if you draw that power angle characteristic, it is something like this. This is, say, 90 degrees and this is 180 degrees. A maximum power transferred, P max, is at delta equal to 90 degrees, because for delta equal to 90 degrees, sine 90 is 1, so it is V square by X. Okay, so this is the maximum power, this is the power angle characteristic, and this is the maximum power transfer capability of the line. However, from stability point of view, we never operate the system at delta equal to 90 degrees. We operate it at much lower transmission angle, around 20 to 25 degrees or 20 to 30 degrees, somewhere here. And that gives us how much power will be actually carried by the transmission line. Now, if you are compensating your line with the help of shunt compensation technique, so for shunt compensated line, the power transferred over the line, the characteristics of the transmission line are modified, and the power transferred over the line is now 2V square by X sine delta by 2. Therefore, maximum power transfer will not take place at delta equal to 90 degrees, because for delta equal to 90 degrees, sine 90 by 2 is sine 45 degrees. Maximum power transfer will take place at delta equal to 180 degrees, because 180 by 2 is 90, sine 90 is 1. And how much power will be transferred by the line at delta equal to 180 degrees? 2V square by X. That is 2 times this. 2 times the maximum power transferred by uncompensated line. And if you draw the characteristic, it is something like this. This is the maximum power carried by the line, and it is 2 times P max, where P max is the maximum power carried by the line, carried by the uncompensated line. A shunt compensated line carries 2 times the maximum power as compared to an uncompensated line. Okay, so this is the graph for uncompensated system or uncompensated line, for which the power equation is given by P equal to V square by X sine delta. And this is the power angle characteristic for compensated line, of course, shunt compensated line. Shunt compensated line, for which the power carried is 2V square by X sine delta by 2. So therefore, for same delta, same transmission angle, a higher power or more power can be carried a particular transmission line if it is compensated by a shunt compensator. So therefore, these equations and these power angle characteristics clearly show that with shunt compensation, the power handling or power transferring capability of an existing transmission system can be increased. So this is the first advantage of shunt compensation, that is, it increases the power transfer capability of transmission line. Fine. The other advantage is voltage. It provides voltage support to improve voltage stability. Voltage support to improve, within brackets I will write, to improve voltage stability of the system. To improve voltage stability. We can understand this advantage of shunt compensation if we take a simple radial system, a radial feeder or radial transmission line. Suppose this is the generating station, and this is the sending end voltage Vs, and this is the transmission line with reactance Jx, and current carried by current flowing is I, and this is the receiving end with receiving end voltage as Vr, and at this receiving end we are connecting a load. This is the load. So this is a radial system, okay, where over a transmission line power is carried, line reactance is Jx. The current carried by the transmission line depends upon the load, and it is I. Sending end voltage or voltage at the generating station or at the generation side is Vs, and load voltage is Vr. So this is an uncompensated transmission line, radial line, feeding a load with load voltage Vr. Now let me draw the graphs showing receiving end voltage as a function of power carried by the transmission line. So this axis is power carried by the transmission line in per unit. Let's take it in per unit. And this axis, y-axis, is the receiving end voltage. And let us take this also in per unit. Now if this is 0 per unit, this will be 0.5 per unit, 1.0 per unit, 1.5 per unit, 2 per unit, 2.5 per unit, and so on. Similarly, this is receiving end voltage is 0.5 per unit, 1 per unit, 1.5 per unit, and so on. Let us see how the receiving end voltage or load voltage changes as the power transferred over the line increases, as the load power increases. And we will draw for different power factor angles or different power factors. So it is something like this. My first graph will be like this. This is the power receiving end voltage versus power for a power factor of let us say 0.8 lagging. This is 0.8 lagging power factor. Okay, let me first of all draw these curves, then I will explain. Next curve is this. This is for a power factor of 0.95 lag. Again, lagging power factor, but improved power factor. 0.8 to 0.95 improvement. And then next curve is for, say for example, it is for unity power factor. This is unity power factor, UPF. UPF means power factor equal to 1. And now let us assume our load is operating at leading power factor, and then we will have power versus receiving end voltage versus power like this. And let us suppose the load power factor is 0.97 lead. Now this is leading power factor. And finally, this is 0.9 lead. 0.9 leading power factor. Okay. Now you can very clearly see that, say for example, 0.8 lagging power factor. If this is the receiving end voltage is unity for zero load, and as the load draws more and more power, or more and more power flows over the transmission line, of course there will be active power as well as reactive power. So Ji into X drop increases more and more, and then voltage drops quickly. Since the load is operating at slightly lower power factor, 0.8 lagging, this current has reactive component Ix because of load operating at reactive, this lagging power factor. So in addition to active component of the power, there will be reactive component of the power. So in one of the earlier classes, a couple of lectures back, I have already explained to you that if you resolve this transmission line current into two components, it will have resistive or in phase component of current, and it will have reactive or quadrature component of current. This resistive or in phase component of current is because of the active power which is flowing over the transmission line, and quadrature or reactive component of current is because of the reactive power which is drawn by the load which is flowing over the transmission line. So out of the two drops, say JIR into X drop, that is the voltage drop across transmission line reactance, which is because of the active power or because of the in phase component of current, and another drop is JIX into X, which is the power voltage drop across the transmission line reactance because of the reactive power flow or because of quadrature or reactive component of current. Out of these two voltage drops, this drop is predominant. This drop does not change the voltage, receiving end voltage much, because this voltage drop is at 90 degrees with respect to sending end voltage, but this voltage directly subtracts from sending end voltage. So therefore your receiving end voltage becomes less than sending end voltage, and more will be this drop, lesser will be the receiving end voltage. So therefore JIX into X voltage drop is responsible for receiving end voltage to be less than sending end voltage or poor voltage regulation. And you can very clearly see that for 0.8 lagging power factor, as the power increases, there is steep drop in the voltage till you reach this point. See, these points, this point, this point, these points, these are called nose points. These are called nose points. Nose points are those points beyond which your system becomes unstable, or beyond which your system is subject to voltage instability, because you can see up to nose point, no doubt for example, for 0.8 power factor lagging, as the power increases, there is steep drop in the voltage, but beyond nose point, your voltage collapses and finally it becomes equal to zero. So nose points basically on each curve represent voltage instability. So if you see nose point basically represents voltage instability of the system, because beyond this nose point, there is a collapse of the voltage. So therefore you cannot draw a large amount of power from the system beyond nose point, because there will be voltage collapse. Okay. Similarly, now if active power is same, but reactive power changes. In other words, if the load power factor improves, it improves from 0.8 lagging to 0.95 lagging. You can see there is drop in the voltage is less as compared to the previous case. Why? Because the reactive component of power decreases, and because reactive component of power is now less, Ix component is less, and this drop decreases, and therefore there is better voltage, receiving end voltage, and the nose point is shifted towards the right. If this was the voltage instability point for 0.8 lagging power factor, for 0.95 lagging power factor, this is the point of instability, or this is the nose point. If the system or if the load is operating at unity power factor, that's power factor equal to 1, then nose point is further shifted towards the right, and the receiving end voltage, there is improvement in the voltage regulation. And now if your system operates at a leading power factor, for example, last two curves you can see, here the load operates at 0.97 leading power factor, and finally here load operates at 0.9 leading power factor. Leading power factor results in better voltage regulation. In fact, it results in increase in the receiving end voltage, large increase in the receiving end voltage. No doubt, as the load increases, there will be drop, but the drop will not be as steep as that for lagging power factor loads. Because when we say leading power factor load, then this means Ix will be ICX. This will be capacitive component of the current, and it will result in voltage drop of opposite polarity. And this voltage drop will nullify the reactive voltage drop. In other words, it will increase the receiving end voltage. So therefore, as we move from lagging power factor operation to leading power factor operation, the nose point shifts towards the right and more voltage stability occurs, and there is improvement in the receiving end voltage. This is for uncompensated transmission line. Now anyway, you can see that beyond these nose points there is collapse of the voltage, whether your system is operating at lagging power factors, unity power factor, or leading power factor. And now if you want to give voltage support, you want to improve the voltage stability, then you have to go for the compensation. And we will go for shunt compensation. Let us see with shunt compensation how the system, this voltage stability improves. So let us go for shunt compensation. This is again sending end voltage Vs. This is the transmission line reactance. This is the line current. And at this bus, what we do is that we connect a compensator, a shunt compensator, of course. This is shunt compensator. Shunt compensator. It may be a capacitor bank if it is passive compensation, or it may be an SVC, static var compensator, or StatCom if it is active shunt compensation using FACTS devices. It depends. And then this is your load. The question is why I have connected this shunt compensator across the load, and this is the receiving end voltage or load voltage. Because in the radial system, the minimum voltage occurs across the load, because this load voltage VR is sending end voltage minus this drop. So since load suffers the voltage drop, so therefore the compensator is connected at a point where there is minimum voltage, or where there is the larger drop in the voltage. So in this case it is connected across the load. But if it would have been a system like this, two bus system, where this was the sending end voltage, this was the receiving end voltage, in that case the best location of shunt compensator was in the middle of the transmission line, because we know for this two bus system, the maximum voltage drop occurs in the middle of the transmission line like this. If this is the distance and this is the voltage, then this is the sending end voltage, this is the receiving end voltage. Maximum drop occurs in the middle, and best location of shunt compensator is middle of the transmission line. But for this case, where we have a radial feeder or radial transmission line, the best location of shunt compensator is across the load, because the load suffers the maximum voltage drop. Now what will this shunt compensator do? It will absorb or generate the reactive power and inject that reactive power into the bus, and it will improve the receiving end voltage. It will provide by injecting the reactive power into the bus, into the system, it will provide voltage support, and hence it will improve the voltage stability. Let us try to understand that with the help of graphs. So again, this is power drawn by the load, or power flowing over the transmission line in per unit, versus load voltage or receiving end voltage, which is also in per unit. So this is 0 per unit, this is 0.5 per unit, 1.0 per unit, 1.5 per unit, 2 per unit, 2.5 per unit, and so on. This is 0.5 per unit, this is 1 per unit, 1.5 per unit. We will operate the loads for same power factors. First of all, 0.8 power factor lagging, then 0.95 power factor lagging, as we have done without compensation, then unity power factor, which means power factor equal to 1. Then we will go for 0.97 power factor leading power factor, and finally 0.9 power factor leading. Okay, so in this case we will have situation like this. This is for 0.8 power factor lagging. So this is 0.8 power factor lagging power factor. Okay, now we can see if you compare this graph with the graph for 0.8 power factor lagging without compensation, there the nose point was somewhere here. It was something like this. Here the nose point is shifted towards the right, because what this compensator will do, it will compensate the reactive power demand of the load, so that the reactive power which is flowing over the transmission line, that decreases, so that JIX into X drop decreases and receiving end voltage improves. Okay, if the load power factor is now improved, say for example it is improved from 0.8 power factor lagging to 0.95 power factor lagging, the nose point is shifted further towards right, and there is better, the drop in the voltage is not steep as was the case without compensation. Then for unity power factor, it will be something like this. This is for unity power factor. Then for leading power factor, for example, 0.97 leading power factor, you can see the drop in the voltage is very, very small, and nose point is also shifted towards the right. And finally for 0.9 power factor leading, you can see the drop in the voltage, the receiving end voltage is almost maintained constant. But if the power transferred over the line is very large, it is 2 per unit, means 200%, then obviously after the nose point there will be collapse of the voltage. So therefore the advantages of providing shunt compensation is, first of all, the load voltage or receiving end voltage is maintained almost constant because of the shunt compensation, reactive power compensation provided by the shunt compensator. And secondly, the nose points or voltage instability points, they are shifted more and more towards the right. So your system becomes more stable as far as voltage stability is concerned. So therefore we have seen that by comparing this graph with the previous graph for uncompensated transmission line, we have found that the compensated transmission line gives better voltage regulation. The compensator provides the reactive power and hence voltage support, because of which there is less drop in the voltage. The receiving end voltage remains very nearly equal to sending end voltage, and voltage regulation is improved. And secondly, the nose points, which represent the voltage instability points, they are also shifted towards the right. So therefore voltage stability is also improved. Another point which I would like to discuss with you is that if we have a number of parallel transmission lines, say like this, we have a number of parallel transmission lines, and if any one of the transmission line trips, suppose there is a fault on this line and it trips, then all the load which was taken by this transmission line, that will be shared by the other two transmission lines which are still in operation, and that will result in voltage depression, because these lines will get overloaded and that will result in voltage depression. I mean there will be a large decrease in the voltage, which is called voltage depression. And if your system, your lines are compensated by shunt compensators, then this shunt compensator will quickly inject the reactive power and it will prevent this voltage depression. There will be no doubt drop in the voltage, but the drop in the voltage will be reduced, and hence the shunt compensator, in the event of fault and tripping of any one of the transmission line, will help in avoiding voltage depression. Okay, so that is about second advantage of shunt compensation, that is it provides the voltage support with the help of reactive power, and hence it improves the voltage stability of the system. Third advantage is improvement in transient stability. Transient stability improvement, I should write like this: transient stability improvement. With the help of shunt compensation, the transient stability of the system is improved, which we could not understand in previous or last to last lecture when we were discussing shunt compensation. Now we will try to understand how transient stability of system is improved. For understanding this, let us take first of all an uncompensated system and draw its power angle characteristics, and then reproduce that power angle characteristics for shunt compensated system, and try to understand how shunt compensation improves the transient stability of the transmission system. So let us first of all take uncompensated system. This is figure A. Figure A is for uncompensated system. Uncompensated system. Right. So this x-axis is transmission angle or power angle delta, and along y-axis I will have power, active power or power transferred over the line. So this is delta equal to 0 degree, and let us suppose this is the power angle characteristic. For uncompensated transmission line, we already know that this is the power angle characteristic. This is P max, which is equal to V square by X. So here power is given by V square by X sine delta, right? And for delta equal to 90 degrees, which is somewhere here, and of course this is delta equal to 180 degrees, this is delta equal to 90 degrees, sine 90 is 1, and maximum power transferred over the line, which is also called steady state limit of the transmission line, is Px equal to V square by X. So this is for uncompensated transmission line, and I should write here P max equal to V square by X. Now, what is the operating point of your system? Let us suppose this is the operating point. My system is operating somewhere here. Let us suppose the mechanical power which is provided by the turbine is equal to electrical power transmitted over the transmission line. So this is the point where my system is operating, and let us suppose that my system is operating at a power angle delta 1, right? So my system is operating at, this is the operating point. I have already told you that you can never operate your system at delta equal to 90 degrees, because if you operate your system at delta equal to 90 degrees, a small disturbance will result in system become unstable, and your system will be unstable always. So therefore you have to operate your system at a power angle much less than 90 degrees, somewhere here. How much is this? This is 20 to 30 degrees, around 20 to 30 or 35 degrees. So my system is operating here, okay, and it's operating at a power angle or at a transmission angle delta 1. And how much electrical power is flowing over the transmission line? How much electrical power is flowing over the transmission line? This is Vs, this is Vr. PE, electrical power, is flowing over the transmission line. Let's call that PE. And it is equal to mechanical input to the generator. The generator has mechanical input, and that mechanical input is equal to electrical output. And this is the power which is flowing over the transmission line. Let us suppose a fault occurs over the transmission line. Fault. And this transmission line trips. Maybe a line to ground fault or a short circuit has occurred. And when a three-phase short circuit has occurred, the line trips. And when the line trips, no electrical power will flow over the line. Electrical power flowing over the line will become 0, but the turbine is still providing the mechanical input. Electrical output has become now 0, but mechanical input is constant. It does not change. Now, since mechanical input is there, but electrical output is 0, what will it result in? It will result in acceleration of the rotor of the generator. So generator will accelerate, and as generator accelerates, delta increases. And let us suppose delta increases from delta 1 to delta 2. It increases up to delta 2 because machine is accelerating. Why it is accelerating? Because it is not supplying any electrical power. Transmission line has tripped. Electrical power output is 0, but mechanical power input from the turbine remains same. That results in the acceleration of machine from delta 1, and the power angle or transmission angle increases from, say for example, from delta 1 to delta 2. As soon as your machine accelerates and delta becomes delta 2, let's suppose fault has been cleared. So fault is cleared here. And as soon as fault is cleared, the transmission line is again reconnected and electrical output power starts flowing. Okay, now the question is, when the transmission line is reconnected, okay, how much electrical power will be flowing over the transmission line? It will not be E, it will be, say, PE dash, which is greater than PM, because your machine is now not operating at delta 1, it is operating at delta 2. At delta 1 it was transferring a power of PE, and at delta 2 you can see the power transferred is this much, and electrical power transferred is PE dash. Let us call this PE dash, and this PE dash is greater than PE, and of course this PE dash is greater than electrical output power, now is greater than mechanical input power, and that will result in deceleration of the machine. So machine will start decelerating, but the kinetic energy, when the machine starts decelerating, it is still rotating. The kinetic energy stored in its rotating parts will still go on increasing. So therefore delta will keep on increasing, say up to this point. Delta 2, delta 3. And now why it will go from delta 2 to delta 3? Why not delta 3 is here? Why not delta 3 is here? You have to understand that. Fault has occurred here. Initially, your system was operating under steady state operations where mechanical input provided by the turbine was equal to electrical output. PE was the power transferred over the line. Fault has occurred here. Electrical output, the line has tripped. No power is transferred over the line. PE has become 0. PM is the same. Mechanical input is same. That results in the acceleration of the machine, and machine accelerates and transmission angle increases from delta 1 to delta 2, and as soon as it becomes delta 2, fault is cleared and line is again reconnected. Now as machine accelerates from delta 1 to delta 2, this area A1 is called, it represents the kinetic energy stored in the rotating part of the machine, because machine is accelerating, and it is accelerating because of higher mechanical input, as electrical output is 0, and this mechanical input will result in acceleration. So it will store the energy, kinetic energy, and that will be represented by this area A1. This is the stored kinetic energy or acceleration kinetic energy. And as soon as delta becomes equal to delta 2, fault is cleared, line is reconnected, and power transfer again takes place. Now how much power will be transferred over the line? It will not be PE, it will be higher, because now your system is not operating at delta 1, it is operating at higher transmission angle delta 2, corresponding to which the power transmitted over the line is not PE, it is PE dash, which is greater than PE, and hence it is greater than mechanical input power. And since electrical power transferred over the line is more than mechanical input to the generator, so machine starts decelerating, and delta keeps on increasing from delta 2 to delta 3. Now the machine will continue to decelerate until the area A2, which represents the decelerating kinetic energy, becomes equal to area A1. This area A1 represents the kinetic energy stored or accelerating kinetic energy. Area A2 represents the decelerating kinetic energy, because from delta 2 to delta 3 your machine is decelerating. Why? Because electrical output is more than mechanical input and decelerating kinetic energy, and there should be balance between the two kinetic energies, that is decelerating kinetic energy. When decelerating kinetic energy becomes equal to accelerating kinetic energy, your system comes back to steady state. It again starts operating at delta equal to delta 1, for which power is PE. The mechanical input power is PM, and electrical output power is again PE, and PM is equal to PE, and machine comes back to steady state. So therefore A1 is equal to A2, and as soon as A2 becomes equal to A1, your machine comes back to steady state operation. Okay, so initially your transmission angle increases from delta 1 to delta 2 when line is tripped and fault is cleared here, then the transmission angle increases from delta 2 to delta 3. During this process from delta 1 to delta 2, machine accelerates, and this area A1 represents the accelerating kinetic energy, and from delta 2 to delta 3 machine decelerates, and A2 represents the decelerating kinetic energy. As soon as this area A2 becomes equal to A1, as you can see, this area becomes equal to this, and that's corresponding to delta equal to delta 3. The machine comes back to its steady state operation, and then it again starts transmitting power PE at this torque angle, at this transmission angle, and PE becomes equal to PM again. So steady state operation again is restored. So therefore this area, this area which is left here, it is called margin of stability. It's called a margin, that is margin of stability. This is very important. This is important in the sense, let us suppose, let us try to understand what is the importance of this margin of stability, a margin, which is this area. It's very important. Again, your system is operating at delta 1, transmission line carries power P, which is equal to Pm, and fault occurs, line is tripped again, machine accelerates because P is equal to 0, but Pm is constant because of this constant mechanical input and 0 electrical output, machine accelerates. Instead of clearing the fault here at delta 2, if fault is cleared here, if fault clearing is delayed, instead of clearing it here, if it is cleared here, then this accelerating area will increase. And for balance, to make A2 equal to A1, decelerating area should also increase so that A2 becomes equal to A1. And this decelerating area may go, beyond this point. And beyond this point, what happens? The electrical power output decreases. It decreases. That means if this is for example, if the situation is like this, if this represents the accelerating area, your decelerating area should be from this to this, but this is unstable. Your decelerating area can be only up to this. When this line touches your power angle characteristic, it cannot be below this. Below this means unstable. So therefore, if the fault clearance is delayed, instead of clearing fault here, if it is cleared late, then decelerating area A2 will never be equal to accelerating area. It will always be equal to A1, and your system will be unstable. It will never be stable. It will never be stable. So that's why this margin of stability is very, very important. Higher this margin of stability, the more stable your system is. Let me redraw the previous. It was delta 1, delta 2, area A1. And this was area A2, and this was delta 3, okay. Now, this is for uncompensated system. So for uncompensated system, the margin of stability is less, which means if fault clearance is delayed by sufficiently large time, then the system will become unstable because you don't have much margin of stability. Now, if the system is shunt compensated, I have same system. This is sending end voltage, this is transmission line with reactance this, but this transmission line is now compensated. This is shunt compensator, for example, shunt compensator. This is receiving end voltage. With shunt compensation, you can now, I will now prove graphically that margin of stability is improved. It's increased. This is again delta versus P. This is figure B. And this is for shunt compensated system. Shunt compensated system. Figure A, this figure was for uncompensated system, in which case power transferred over the line was given by this equation, P equal to V square by X sine delta. For shunt compensated system, which I will show in figure B, the power transferred over the line is 2V square by X sine delta by 2. So let me draw the graphs again. This is again delta equal to 180 degrees. This is uncompensated, same graph I am putting here. But for compensated system, shunt compensated system, the graph will not be given by this. Power angle characteristic is not given by this. It is given by something like this. This is the power angle characteristic. This is for shunt compensated system. Shunt, we already know it, we have studied it in one of the previous classes. This is shunt compensated system for which power is 2V square by X sine delta by 2. So your power angle characteristic gets modified for shunt compensated system. Instead of having this is your new power angle characteristic. And let us again assume that our system is operating, say, at delta 1. Initially it is operating at a transmission angle delta 1, where electrical output is equal to mechanical input, P is equal to Pm, And let's again assume that a fault has occurred here in the system. As soon as fault occurs in the system, the line is tripped, the electrical output is zero, mechanical input is same, it's constant, machine starts accelerating. And as the machine accelerates, for example, it accelerates, the transmission angle increases. Let's call this P, delta P1 to delta P2, because here I have written delta 1, delta 2. To differentiate between the two, I will call this delta P1, delta P2, and this is area AP1, which represents the accelerating kinetic energy. And as the transmission angle increases because of acceleration of the machine, as the transmission angle increases from delta P1 to delta P2, we assume the fault is cleared and line is reconnected. It again starts transmitting the power, but how much power will it transfer? It will transfer higher power. So mechanical input is same, electrical output is higher, PE dash is greater than PE, and it is greater than PM. So machine starts decelerating, and as machine starts decelerating, this delta will keep on increasing, and you can see machine starts decelerating, and as soon as your transmission angle reaches delta P3, the decelerating area or decelerating kinetic energy, which is represented by area AP2, is exactly equal to accelerating kinetic energy. The two will balance. So AP at delta equal to delta P3, AP2 is equal to AP1, that is deceleration kinetic energy is equal to acceleration kinetic energy, and system comes back to steady state operation. Now the question is, how much is the margin of stability left? If you see, your graph, this is not an uncompensated system. For an uncompensated system, the graph was coming down and your margin of stability was only this much. But for this compensated system, this is your graph, power angle characteristic, और आपके पास कितना बचता है, how much is the this margin of stability. ये सारा area बचता है. This whole area represents the margin of stability, which we call as AP margin. So margin of stability is very, very large. That means even if your system fails to clear fault here, it clears fault very late, the system will still remain stable because it has a very large margin of stability. It will never become unstable. Okay, for a delay in the fault clearing, even if there is a large delay in the fault clearing, since margin of stability is very large, a larger area is left as a margin of stability as compared to uncompensated system where margin of stability was very, very small. So your system, it ensures that the system remains stable, that transient stability of the system is improved. So therefore we can say that the margin of stability, AP margin, for a compensated system is much, much greater than margin of stability, A margin, for uncompensated system. This is the margin of, this whole thing is the margin of stability, A. For shunt compensated system, it is much, much greater than margin of stability, A margin of uncompensated system. So therefore this proves, or we have proved graphically, that a shunt compensated system improves the margin of stability, which means that it improves the transient stability of the system. The system becomes more stable. Okay, so I hope this is clear to you. And then another advantage of shunt compensation is power oscillation damping or electromechanical oscillation damping. It's called power oscillation damping, or it is also called electromechanical oscillation damping. First of all, we have to understand what results in electromechanical oscillations or power oscillations and how shunt compensation helps in damping of those oscillations. For understanding this, we will draw certain diagrams, graphs. So for example, this is time axis and this is the transmission angle or power angle delta. Let us suppose my system is operating at a steady state value with a transmission angle delta naught. And suddenly some disturbance has occurred, and this disturbance results in oscillation of this transmission angle. The transmission angle may increase, it will become greater than steady state value, and then it decreases as soon as it becomes equal to steady state value, then it decreases further, it becomes less than steady state value, then it again increases. So there are oscillations around the mean position, around the mean value. So these are the oscillations of transmission angle or power angle around its mean value because of some disturbance. What is that disturbance? That we will try to understand with the help of next graph. This is the next graph where I will show that what causes this oscillation. Let us suppose the power transmitted is P naught. When system was operating at steady state at a transmission angle delta naught, it was transmitting or transferring power over the transmission line equal to P naught, steady state value. Okay, and let us suppose some fault has occurred, or some disturbance has occurred, which has momentarily reduced the power transferred over the line. So the power transferred over the line is reduced momentarily maybe for a fraction of a second. As soon as P decreases below P naught, that is power transmitted over the line decreases. Mechanical input is same, electrical output has decreased, it has become less than P naught steady state value. So that means mechanical input now becomes greater than electrical output and machine accelerates. And I have already told you when machine accelerates, delta increases. So d delta by dt becomes greater than 0, and that's why here this delta, when machine accelerates, d delta by dt becomes greater than 0, and there is increase in delta. And we know that when delta increases, the power which actually the system must transfer, that also increases, because the power transferred is directly proportional to sine delta. When delta increases, P should also increase. So therefore there will be oscillations in the power also, like something like this. The power transmitted, the power which should be transmitted, it should increase. And then as delta reaches some maximum value, and then it decreases, because a fault thodi der ke liye aaya, there was a small disturbance, and then disturbance is gone. So after this time disturbance is gone, but your system oscillates. Your system does not come back to steady state value. You can see because of this small disturbance, when P became less than P naught, so that Pm was greater than P dash, the machine accelerated, which caused increase in delta. D delta by dt was greater than 0, and acceleration resulted in increase in delta. And then when system came back to its normal value, P naught फिर से restore हो गया, then it should have come back to delta naught. But what happens? The system is subjected to oscillations. फिर ये oscillate होता है, it becomes less than delta naught, then again greater than, and there are sustained oscillations, and this results in power oscillations also, like this. These are the power oscillations, something like this. Okay, so these are called electromechanical oscillations or power oscillations. Now how to damp these power oscillations? Because these power oscillations will be, these electromechanical oscillations will be like this. From here to here, d delta by dt is greater than 0, and then from here to here, d delta by dt is less than 0. That means machine is decelerating now, and when machine decelerates, delta becomes less than delta naught. Okay, and then it again accelerates, then again d delta by dt becomes greater than 0, और एक चलता रहता है, and your machine keeps on accelerating, then decelerating, and again accelerating, decelerating. It is subject to sustained electromechanical oscillations, and that may result in power oscillations like this. It does not mean that the power transferred over the line increases or decreases like this. Machine is unstable, sort of unstable. It is subjected to electromechanical oscillations, which we have to damp out very quickly. How to damp? For that purpose, we will use shunt compensator. And how will this shunt compensator help in damping of these power oscillations? That's very interesting. You can note down from here. Let me first of all draw these projections, then it will be clear. as soon as there is some disturbance in the system, the electrical output decreases. I mean the power transferred over the line decreases. जिसकी वजह से ये because mechanical input was greater than electrical output, because you can see electrical output is decreasing due to some disturbance. There was d delta by dt was greater than 0. There was acceleration of the machine, and which caused d delta by dt greater than 0, which caused delta to increase above its steady state value. Now if I want that machine should not accelerate, so that delta should not increase, what should shunt compensator do? It should inject the reactive power into the system. This is the reactive power injected by the shunt compensator into the system. It should inject certain amount of reactive power into the system. When it injects the reactive power in the middle of the transmission line, because shunt compensators are generally connected in the middle of the transmission line, and we know that when shunt compensator is there, it increases the power handling capability of the system. The power transfer capability of the system is 2v square by x sine delta by 2. So that means more power, electrical power, will be now transmitted or transferred over the transmission line, more than what it was carrying when the system was uncompensated. So as soon as the shunt compensator injects the reactive power into the system, the line carries more electrical power. And when line carries more electrical power, let's call that P0 double dash, which is greater than P0 dash. PM is still greater than P0 double dash, लेकिन ये difference कम हो जाती है. उसकी वजह से machine की acceleration कम हो जाती है. और जब machine की acceleration कम हो जाती है, delta will increase, but it will increase to a smaller value. ठीक है? After this point, what happens? आपका डेल्टा अब डिक्रीज हो रहा है. ये देखिए डेल्टा डिक्रीज हो रहा है, क्योंकि अब मशीन इसके बाद डिसेलरेट होना शुरू हो जाती है. ओके, इन ऑर्डर टू अवॉइड दिस डेल्टा बिकमिंग लेस देन डेल्टा नॉट, डिसेलरेशन कम करने के लिए, व्हाट शुड योर कंपनसेटर डू? इट शुड इंजेक्ट negative reactive power. I mean here it was injecting the reactive power. Now it should, negative reactive power means it should absorb the reactive power. It should act as an inductor. And when it acts as an inductor, the power transferred over the line decreases. During this period, the power transferred over the line increases, and from this point to this point, the power transferred over the line should decrease. Why it should decrease? क्योंकि आपकी machine अब decelerate होती है. Decelerate machine तब होती है when electrical output is greater than when electrical output is greater than mechanical input. Here your compensator has injected reactive power, and that has increased the electrical power transferred over the line. No problem, and it has damped oscillation to some extent. लेकिन उसके बाद delta decrease होना शुरू हो जाता है. You can see it goes negative. I mean it goes small, not negative. उसका मतलब ये हुआ, when will delta decrease? Delta will decrease only when machine decelerates. And when will machine decelerate? When electrical power transferred over the line is greater than mechanical input. तो उसको बैलेंस करने के लिए your compensator now absorbs the reactive power. Negative reactive power here means it is now absorbing the reactive power. That means it is acting as an inductor. And when it acts as a, here it was acting as a capacitor. Now it is acting as an inductor. And when it acts as an inductor, it absorbs the reactive power. उससे the power which is transferred over the line decreases. Here it was increasing, now it will decrease. The electrical power transmitted over the line decreases. So it is now P0 triple dash, which is less than P0 double dash. And this decreases to the level that it becomes nearly equal to mechanical input. उससे क्या होगा? मशीन की डिसेलरेशन हो जाएगी, लेकिन वो डिसेलरेशन कम हो जाएगी, because electrical output is not very larger than mechanical input, because the negative reactive power injection means your compensator is acting as an inductor. It decreases the power transferred over the line, electrical power. And when less electrical power is transferred over the line, there is a balance of mechanical input and electrical output. तो ये oscillation फिर से कम हो जाती है. उसके बाद फिर से जब acceleration शुरू हो जाती है, again it injects positive reactive power, becomes positive, negative. It continues like this till oscillations are damped. तो ये पहले साइकिल में ऑसिलेशन है डेल्टा की, दूसरे साइकिल में और कम हो जाएगी ऑसिलेशन, तीसरे साइकिल में और भी कम हो जाएगी ऑसिलेशन, और फाइनली द ऑसिलेशंस आर ओवर. देयर आर नो ऑसिलेशंस इन डेल्टा. So this is for undamped system. There are electromechanical oscillations. Delta is oscillating if there is no compensation, and this is for this is damped oscillations or damped system. When you are compensating your system with shunt compensator, the oscillations are damped. So since oscillations in the delta are damped, oscillations in the power will also be damped. Still less oscillations, and finally no oscillations in the power. So this is undamped system and this is damped system. So therefore shunt compensator very quickly, as soon as there is disturbance, electrical power decreases, it quickly injects the reactive power, it increases the power transmitted or transferred over the line, it damps the oscillation, and then it decreases from here to here, it decreases the power transferred over the line, further damps the oscillation, and it continues like this in a bang manner until all the electromechanical oscillations after 3 or 4 cycles are over, and system comes back to its steady state operation, operates at delta equal to delta naught, and power becomes equal to P naught at the end of oscillations. So therefore you can see this is the reactive power which is injected into the transmission system by shunt compensator like this, and finally when the system comes back to its steady state operation, this reactive power injected becomes equal to 0. This is if you are using this shunt compensator for electromechanical oscillation damping. अगर आप उसके लिए use कर रहे हो, then this is how it will quickly damp the oscillations. So therefore your shunt compensator acts in a bang manner. It acts or works in bang manner. Positive, negative is bang manner, and finally it becomes equal to 0 and all oscillations are damped. So therefore I have shown with the help of these graphs that a small disturbance will result in electromechanical oscillations and hence oscillations in the delta, power oscillations, and how a shunt compensator quickly damps these oscillations, electromechanical oscillations or power oscillations, and brings system quickly back to its steady state operation. So this is another advantage of shunt compensation. So therefore we have studied about 4 advantages of shunt compensation. Number 1, a shunt compensator increases the power handling or power transferring capability of an existing transmission line. Number 2, the shunt compensator provides the voltage support and hence improves the voltage stability of the system. Number 3, a shunt compensator improves the transient stability of the system. And finally, a shunt compensation or shunt compensator quickly damps the electromechanical oscillations. It results in electromechanical or power oscillation damping. So these are the advantages of shunt compensation. So I hope this is clear. Please go through this lecture. In case of any doubts, put your doubts on the group or on the YouTube channel. I will be happy to clear your doubts. Inshallah, in next lecture we will study the advantages of series compensation. Please go through this lecture and all other previous lectures, and in case of any doubts, I again repeat that please put your queries on the group or on the YouTube channel. I wish all the best to all of you. Thank you.